we should make sure we record this joke. Okay. Josh, are you ready for the joke? Yeah, that's a la Aiden and Andy this morning. Okay.
I'm not surprised.
Yeah, you can feel free to go and redo that joke over there if you want. I don't know. Yeah, so are you ready for a joke? This is really a really excellent joke that you'll want to use in all your parties. Okay, here we go. And what would this unit be without a polar bear joke? Here we go. Okay, do you know what a polar bear is? Have you heard this before? This is a very common joke. Okay. Well, it's pretty obvious. It's just a regular rectangular bear. After it changes coordinates. Come on. You didn't laugh at all, Taylor. Not even a little bit. Go back to drinking my chai tea. Okay. All right. What is in there? Who knows? What is in there? Tea. What kind of tea? I was like, that would be really spooky if I guessed right.
I think it is right.
Ah, man. Profit, okay. Polar systems is what we're going to talk about today. And so we're going to graph some systems and find intersection points, things like that. So I'll try to make it interesting. We'll see. All right. Let's start with the one that I think the graphs are easy. Let's graph these, and then we'll also think about what it would mean for us to think about intersections. There's maybe a little bit of the graph here is easy, but then we have an interesting discussion that goes with it. So I think we can graph this, even though you've never done r equals. Well, I think maybe there was one in the homework, right? We haven't really discussed this kind of equation very much, but what is this? R equals 4. It's a circle, 1, 2, 3, 4 of radius 4. Here we go. There it is in blue. Yay. Okay. And then what's your other favorite color? We do green. I like green. Okay. All right, and then green will do this, which is what? What's that kind of graph? What is that? Are we getting good at this, hopefully? It's a rose curve with 4 petals of like 4, right? And they're pointed in, what's the very first one? Yeah, the first one's in the 0 direction, right? And then the others, so they're all pointing up, down, left, right, someone said, yeah. All right, so we go through all these points. Here we go. The fun part. Try to make them pretty, on your quiz tomorrow. If I'm going to ask you to graph something, you're going to try to make it beautiful. Okay. Then you might also think, well, wait a second. Do I really have to graph that? That's a good question. Maybe I can approach this algebraically. I know what it means to solve for the intersection points between two curves in rectangular coordinates. We'll be setting them equal to each other and solving. So let's do that. Let's do that. Here we go. It's so fun. I love it. Okay. All right, so 1 equals cosine 2 theta is the equation I end up having to solve here. And that requires that 2 theta be, having this discussion again like we did on the board over here earlier. 2 theta better be pi over 2, 0. And pi, and some other things, right? I won't need to, and we could list the other ones too, right? 2 pi. We can list a couple, but we are only going to give a limited domain here. So what do we get? 0 and pi over 2 and
You have to add 3 pi's and 2.
I'm sorry. We just failed there. We're thinking too far ahead here. When is cosine 1 at 0 and at 2 pi and at 4 pi, etc., right? That's the only time cosine takes on the value 1 is at 0 and then again at 2 pi and then at 4 pi and then 6 pi, or 4 pi and then 6 pi and 8 pi, etc. So that gives us at pi, and this will be at 2 pi, but we're not going to include that one, right, on this interval. So we only get 2 places that
there are only two solutions to this equation on that interval, 0 and pi for theta. And for both of them, our r value is 4, right? So here are the intersection points. 4, comma 0, and 4, comma pi. But, of course, intuitively, you're like, wait a second. That doesn't seem to be all, right? So we need to introduce now also the notion of common points, which is, I don't know if this is universal language or not, but this is just what we're going to agree to call them. We're going to call an intersection point a solution that arises not just in the picture, but also from the algebra, okay? So if you were to do this just from the algebra, and you weren't looking at the picture, this is what you would get, and you'd be like, you're moving on your way. But then someone might stop you and say, oh, but here's the picture, what about this and this? That's not listed here, is it? So we're gonna we want to like give those points like some cred too somehow. Like we want to like recognize them, you know. So we'll call them. How about we call them common points? Because they're not intersection points, and you'll see. We'll graph this in a second. So we'll call these common points. In fact, all 4 of these points we might consider common points, but we'll just go out of our way to say that these are common points. And what do you want to name them? Well, this is, I don't know. You want to call this 4, comma pi over 2. And the other one 4, comma 3 pi over 2. But I want to be clear, right? These are not solutions to the system, are they? I mean, in the normal sense, like this 4, comma pi over 2 does not satisfy the green equation, right? I mean, plug in pi over 2, you'll get -4, not 4, right? Yeah. So if you're not seeing this yet, I might use kind of the time analogy, right? These hit at this point at 0, 4, comma 0. The 2 graphs are there, and they are there at the same moment in time, kind of, right? And same here. So let's watch this happen. Get out your calculator. I think this is helpful to see these graphs. And put your calculator in simul mode. Okay, if you haven't done this, so that you're graphing these 2 curves are in R. We're going to put R in R1 and R2, these 2 equations. And put this in simul mode so they'll graph at the same time. Then you'll see it, right? So we'll do 4 and 4 cosine of 2 theta. Okay, here we go. Don't ruin it yet. Okay. I know, everyone's already graphing it. I wanted to do it. All right, here we go. I'm gonna make the little, the little ball thing. Here we go. So they're there at the same time. Oh, wait, what happened there? Oh, man. Okay. And then wait. Boom! All right, and then, sorry. And then here they come. There it is, okay. You see how this works? Okay. Isn't that wonderful? I used -4.5 to 4.5. And on X, I used -6.8 to 6.8. I hit zoom square to produce that, right? So that it produces a nice circle. But I know, I was ready for you before you came in. Okay, yeah, Fonda. Yeah, they're not like intersections in the proper sense, right?
It's just like when you graph it, they hit each other at the same time, so it's like they don't.
Yeah, that's what we'll say. And so how do you figure out what a common point is? You have to graph it. That's like our method, okay? Right now. I mean, we could maybe you could think of a more rigorous way of doing it. Maybe. But it's tricky, maybe. Yeah, so we'll just go by the graph, and at least in the context of this class, we'll just like call that good. Try to give you things where the common points are things that are obvious and nice on the graph. Right? So otherwise, I don't know how to name them. Someone else have a question back there? No. Let's do another one. And actually, I'm going to change this problem here. We'll make this sine and sine. I thought we did this last period, and I thought that was fun. Okay. Just because I feel like I have this preference for cosine and y. Okay. Make it more interesting. Not that much more interesting, actually. Okay. So same deal. Let's graph these in our 2 favorite colors. What colors do you like, Irene? What colors should we do? Purple. What should the other color be? Irene's picking the other color. What are these? Well, you have to pick the other color too. I'm giving you this like privilege. You know, it's just, there's a lot of power. I know. Blue. Oh yeah, purple and blue. That's what we'll do. But what are these? Both of them are limaçons. Okay. Ha ha ha. Okay. Shout out to the French teachers. Okay. 1 plus 2 sine theta. That has a max of 3 in the pi/2 direction, right? 1, 2, 3. And a minimum, that has an inner loop, doesn't it? Has a minimum of -1, right? So that's in the 3 pi/2 direction. Oh wait, kind of actually in the pi/2 direction. And it has, if theta is 0 or pi, we get 1, right? All right, so I'm getting the picture of this, and here comes the fun loop-de part. And it goes through the hole too. All right, that's decent. All right, good enough. And blue for this guy here. How about 3 minus 2 sine theta? That's got a max of 5, right? In the 3 pi/2 direction? Yes? So 1, 2, 3, 4, 5. And a minimum of 1 in the pi/2 direction, so that's actually here, okay? And 3 in the other direction. 1, 2, 3. 1, 2, 3. All right, so here we go. Looks something like this, right? I don't know, right? How do you like that? Now let's do the algebra part. And by the way, I'm giving you nice examples here, but obviously, both the graphing could be more complicated. I could make it more interesting, maybe. I'll give you one of these guys. Right. That'd be fun. Yeah, we can do some cool stuff if we wanted. And also, the algebra part could be tricky too. It's not bad here, though. I think you'll find, right? But we'll set these equal to each other and solve. You can imagine, though, that in this process of solving, we could give you some kind of algebra could arise that we saw in the first semester, right? Where you have to use some trig identities, do factor some stuff. We're keeping it pretty tame right now, though. But right, just collect like terms and stuff. What do we get? 0 equals 2 minus 4 sine theta, and conveniently this works out nicely here. Let's see. So we get sine theta equals 1/2. And that means that theta equals, and we're staying on this interval again, 0 to 2 pi, not including 2 pi. So that'd be, maybe you can even kind of make some guesses from the picture. That's pi/6 and 5 pi/6 and some other things, but not things that are on that interval, right? So, no, we also actually have to maybe think hard about what the r value is in each of those cases, because my picture is not great necessarily. So, plug in pi/6 to either one of the equations. Doesn't matter, right? Since, we could check. It should be the same thing. Right? So what was it? If sine of pi/6 is 1/2, we just said times 2 is 1, plus 1 is 2, right? And you should get the same thing if you plug in pi/6 into the second equation, right? So one intersection point is 2, pi/6. And the other is 5 pi/6. If we plug that in, I feel like we should also get 2, yes? Do you? Of course you do. All right, so those are my 2 intersection points. And then do we have any other common points too? We do have this one here, which we were kind of excited about when we even first started. We were like, hey, look at that. But it actually turns out not to be an actual intersection point. It's a common point. Maybe we should graph these simultaneously again. That would be fun. Yeah, Helen?
Wait, how do you know when you're graphing how far
So, like the purple one,
Yeah.
right? So the purple one, we said the max is 3. Do you agree with that? The maximum this expression will ever be for r is 3. Yeah, and when I say 3, I'm thinking like first semester. I'm just thinking about like the expression 1 plus 2 sine theta. I know 2 sine theta ranges between negative and positive 2. So what does this range? The whole thing range between, well, positive 3 and negative 1. And if the answer, if we get a negative and a positive number, then we're creating 2 loops. And the outside loop here will be 3. You can think that'll happen when we're in the pi/2 direction. And when we're in the 3 pi over 2 direction, that's when we get -1 for r. So in the 3 pi over 2 direction, we're actually up here, right? So that's a little weird, but we're okay with it. And so that other common point, how do you want to name that? There are an infinite number of ways of naming polar coordinates, but we'll say that it's, how about 1 comma pi over 2. All right? And like I said, actually, technically, all 3 of these points are common points, right? You know, maybe if we had a Venn diagram, intersection points would all lie inside of common points, you know, but whatever. It's really just a grammatic discussion. We just want to like somehow acknowledge that this is happening somehow. So we'll give it a name. Let's call them common points, right? There's nothing, you know, inherently special about those names. All right, that's cool. Yeah, I would like to just see this because I think it's fun on the calculator. I would like to see this. 1 plus 2 sine theta and 3 minus 2 sine theta. And what would be an appropriate window this time around? I'd like y to range, I'd like y to go up to 5, right? And maybe from -5 to 5 or something. How about -5.5 to 5.5? And then I'll do zoom square. All right, you ready? This is the big show. Boom. Not there though. Nope. Not there. Everyone say. You weren't very excited, okay? But that was the moment right there. Not there though. Well, yeah, we could wait. We could make it send it around a second time if we want, right? Make theta. You want to have it keep going? You can do that. All right. Okay. So questions so far? That's kind of the big idea. You're really actually right now you're preparing to do homework, but I thought I'd throw one more little fun little example up there too. Why is it not an intersection point? Well, we can demonstrate that it's not by plugging in pi over 2 into both equations. If you plug pi over 2 into this equation, the purple equation, what do you get? What do you get? That's all you can get into give me? Well, you tell me. I haven't actually done it yet. Let's see. If you plug pi over 2 into the purple equation, what do you get? Huh? She'll, I mean, we don't think about it. And if you plug pi over 2 into the second equation, in the blue, what do you get? All right, we'll leave it a mystery. No one knows. But they might not be the same thing, right? Okay. Yeah.
Did you say that the graph that's not a common one in the text, they never gets that point because it's executing the...
Are you talking about the point right here, 1 comma pi over 2?
Yeah. So
Yeah, like it's not an intersection point.
It's technically a negative one.
Well, you could also call it -1 3 pi over 2. That'd be okay.
But since they're the same thing, is it technically...
Well, they are kind of the same thing visually on the graph, right? But they're not the 2 different points we said, neither of them are solutions to both of these equations simultaneously, right? Like 1 comma pi over 2 is not a solution to this equation, to both of these equations. Is that true? Right? Does that make sense?
So is it technically a common point?
It's a common point, but it's not an intersection point because it doesn't arise from the algebra, right? Like if you plug pi over 2 into these equations, you do not get 1.
No, I'm saying,
right?
like, does the graph technically hit 1 comma pi over 2, or does it technically not? Because it's not...
Which graph?
The purple one. This is technically not unique.
Yeah, what happens on the purple graph? No one. Let's actually plug them in. If you plug pi over 2 into purple, what do you get? 3, right? So this is not a solution to the purple equation, right? So that's what I said. There's something wrong with this. So you'd maybe like to rename this point. Let's rename it -1 3 pi over 2. Ah, that fixes everything. But then that doesn't satisfy the blue equation,
I'm
right?
saying, look,
Yeah.
it's technically not a... Is it technically a common point because it's not... Purple graph's never actually hitting that point. getting negative.
The purple graph does go through this point, just not with that name, right? It goes through the point -1, 3 pi over 2, like you said. But those are the same point in rectangular coordinates, right?
So
Does that make sense?
Did you like redefine polar graphs so you could have like edges on them?
Yeah, you're asking like how could you get this so that it is an intersection point?
No, I'm saying like because of the different nature of polar graph, would the equations themselves have to have a different nature because the graph is different? Or would it satisfy at least?
What do you want? What do you want to have happen? That isn't happening now. You don't like the fact that common points arise, and you want to fix that situation. Is that what you're saying? Or you?
Yeah.
Yeah.
Why they're
They're arising because of the stuff we just said. Like for instance, here, graph this on your calculator. R equals 4 and R equals -4, right?
Yeah.
Right. Those are two circles of radius 4, but they have no intersection points, right? There's never a time when r comma theta, even though there are an infinite number of common points, right? Isn't that weird?
Yeah.
Is that okay? I mean, so how can we avoid that? I don't know. I mean, we can't really, right? Is the answer. If you convert these back into rectangular forms, then you don't have rectangular form. You don't have this issue. But then, of course, finding the intersections in rectangular form is almost impossible. Yeah. I don't know. Is that satisfied? I don't know. It's not. It's weird, right? I agree. I don't know what else to say. Josh.
I was gonna say how I thought about this.
Okay.
Like you have two planes flying their equations, like one plane is flying the route of one equation, the other one the other one.
Yeah.
Like the points that they crash on would be the intersection.
Absolutely.
The points that they pass.
Yeah, and that's why I like the little bubble thing, the little bubbles on the calculator. It shows right there, boom, they crash. Exactly. But they don't actually crash at that point right there. All right, let me show you one more interesting problem, which I don't know. I like it because it's the kind of thing that is useful, especially as my calculus students have to do this, and we don't really talk about it a lot here. So I have pictured here one petal, just one petal of this rose curve. And I'd like to figure out if you were to, let's not use the calculator, but if you were to go and use the calculator, what would your theta min and max be? In fact, I produced this earlier this morning in a program. So I must have known, right? How did I do it, right? What was my theta min and my theta max is basically what I'm asking. If you were to try to get this picture on your calculator, you put this in R1, then for theta min and theta max, what would you make it be, and how would you figure it out? Everyone think about that for a second before you answer. I know I'm asking it in kind of a weird way, but that's what I'm asking. Notice this is a different question to asking when does the petal have its maximum, right? I think the answer to that is when theta is 0, right? We get a petal. But I want to know, when does the petal start and end for theta? I need like a method of analysis here, not just guesses. But let's see, what is true about petals when they begin or when they end? Let's see if,
So since r has to equal 0 when they start and they end, you said like you just put r as 0, but you have to like make sure it's the right one.
yeah,
I
there are
guess.
lots of times when R is 0.
Yeah, so you have to like find the ones that are like just, I don't know how you would do it like mathematically, but like think about it from like the perspective. So here
Yeah.
it would be like the first.
So we'll cross that bridge when we get to it, but I think that's the first helpful hint, right? It's like, let's think about the fact that petals start and end anytime R is 0, right? If you're at the origin, that means you just finished a petal and you're starting another one, right? Isn't that what that means? You came back home. Then it just finished a petal, you're about to start a new one.
and now you're back home, you're gonna just finish that one, you're gonna start a new one, right? Yeah. Well, no, I want a range of values that produce this pedal. It's certainly true that 0 is when you get the max, that's what puts us here, right at the end of this pedal, right? But I'd like to know what range of theta values gives it to us. So I'm gonna find lots and lots of values. There's an infinite number of times when R is 0. So that's good. Let's find them all, and then we'll figure out which ones make this pedal, okay? And in between any two times theta is 0, and then when R is 0, and then later when R is 0 again, the very next time, a pedal happened in between those two times, right? Right? Can you imagine? Okay. So when is cosine of 5 theta equal to 0 is the question. So 5 theta equals pi over 2 and 3 pi over 2, 5 pi over 2, etc. Okay. And also actually, plus or minus all those things if you want, right? So that means that like between, okay, well here, let's divide by 5 and then we'll have our discussion. Plus or minus pi over 10, plus or minus 3 pi over 10, plus or minus 5 pi over 10, aka pi over 2. Okay? So that means like in between pi over 10 and 3 pi over 10, we form a pedal. And then in between 3 pi over 10 and 5 pi over 10, we form another pedal, the next one. And then in between 5 pi over 10 and 7 pi over 10, we form the next pedal, right? Do you see what I'm saying? Okay. So now let's ask the question again. When do we produce this pedal? And there are actually multiple ways. I said give possible values, but give the most obvious one if you want. So that would be probably.
Plus or minus pi.
Yeah, how about plus or minus pi over 10, right? That's a beta. Right? And then maybe you can think of some other times when that happens, right? That's fine though, I just asked you to give one set of values. Because eventually we'll make this pedal another time, right? And another time later as we go on. But that'll work. Does that make sense? So now if you want, feel free to check on your calculator. Graph this in R1, and for theta min and theta max, make it negative and positive pi over 10. And see that you do in fact get this picture, right? Yeah. David?
Wouldn't you just add 2 and pi to each of those?
Yeah, so I have to think about this carefully here. So
N is the same for both
2 n pi to
of them. To get alpha theta.
2 n pi over 5, I think, maybe.
Oh yeah.
Right? Because you're adding 2n up here,
So you're adding
and then you're dividing it by 5, right? Up here, sorry, yeah.
Oh.
Yeah. So, but yes, I think that's how you could do it. You could get some other ones. So try that on your calculator. Let's just test David's hypothesis here. If you add 2 pi over 5 to both of these, try that and see if you get the same pedal. If you add 2 pi over 5 to both of those. Yeah.
I think because I just knew it started at 200, like, at the car, and then just kind of did this.
Mm-hmm.
So when it reaches 0, it's about 10, so you have to work backwards to get to 0.
Yeah, and no, I think it's not obvious to other people maybe that that's pi over 10 though, right? They'd have to actually think this through a little bit. But it is true. I mean, we probably could have ignored these other ones, right? We can maybe see where this is going. Absolutely. Okay, so before you leave, I need to give you a worksheet. Don't run away. The homework, there's a back to the worksheet. Wait, you see it. And this is tonight, the homework is just the worksheet. Yeah. No book problem.
I'm not gonna be here tomorrow. Can I reach you before the next week, Mr. Chase? Like, I'm not gonna be here tomorrow, I'm gonna be in
Yeah. It's like not really a point for your application. But you can just like say in your application like, oh, it's like 16, 18, 19, all of them. He was like,